Hello, we are Design Group 3, and we will be presenting the design specifications of our rehabilitative exoskeleton device. Immobility is a burdensome condition that affects more than 100 million people a year and can lead to costly complications. Traditionally, patients with physical impairments go to rehabilitative therapy to restore function. However, the excessive costs and lack of rehabilitative specialists are factors that affect adherence to these programs. Alternative approaches must be considered to lower costs, lessen the demand on rehabilitative specialists, and improve access to care. One way to address these challenges is through at-home therapy that uses robotic exoskeletons. These are wearable devices that enhance physical performance. This approach relies on assist-as-needed algorithms that use sensors to determine when patients physically need help to complete therapeutic exercise. In order to design the problem statement, a questionnaire survey was administered to 18 people regarding assist-as-needed exoskeleton devices. The general consensus was that these devices for rehabilitation can be uncomfortable, rigid, heavy, bulky, and expensive. To increase patient care and comfort, exoskeleton devices should be redesigned to be more lightweight, user-friendly, and inexpensive. Benefits of this redesign would lead to increased access to care at a lower cost.
The current gold standard in the exoskeleton market is the modularity concept for usability and personal use. This concept allows for more flexibility and variety in the device through the addition of more degrees of freedom. There is currently a growing need for medical and industry-related purposes, since industries want to support employee health along with boosting productivity. Meanwhile, there is an increased amount of spinal cord injuries and other medical disorders that negatively impact limb movement. The current products in the 2022 market have a size of $334.5 million and 11,333 units. And the prominent companies include Exo Bionics, Hokoma, Lockheed Martin, SuitX, Rex Bionics, RB3D, Rewalk Robotics, Cyberdyne, and ActiveLink. These companies all make different kinds of exoskeletons, where some designs are wearable body robots, whereas others are more focused in specific areas of the body, such as the arm, wrist, and leg. There's a large range of current products out there in the exoskeleton market. Through further market analysis, it was determined that mobile exoskeletons dominated the market with a share of 61.1% revenue and 62.2% volume in 2020, and the rest of the market is fixed or stationary devices. Since there is an extreme and growing need for more advanced medical devices for the aging and disabled population, there's an upward trend in the exoskeleton market as reflected by the figure on the left side. In this figure, it also reflects the split in the market between mobile versus fixed exoskeletons in the United States. Meanwhile, the figure on the right, it shows how the global exoskeleton market is split into three, where the majority of the usage is in healthcare, followed by the industry and then military. The global exoskeleton market was valued at $257.9 million in 2021 and is projected to grow by 18% from 2022 to 2030. And this is reflected by the pie chart figure on the right.
A survey was sent out to existing users regarding information about themselves. It was found that most people who needed the exoskeleton device were a part of the working class and around the ages of 30 to 40. It was also found that people working in the industry had the most need for this device. Competitive benchmarking was done on 3 devices: the Myoma MyoPro, Shoulder X passive arm support, and the Carbon Hand device. All of these devices came out on the market within the past 3 years. Exoskeleton devices for rehabilitative purposes are a relatively new concept. Strengths found throughout all 3 devices that were considered for this device are that it is custom fit, adjustments can be made to optimize comfort, and having a rechargeable battery. The main weaknesses found that were heavily considered in the design process of this exoskeleton device was the bulky design of some of these devices. After benchmarking these competing products, there are competitive advantages for this device when compared to others. A lot of devices on the market are used more as a brace rather than an exoskeleton device that moves on its own. Our device will be chargeable to be able to be charged to last all day. The process for obtaining the device will be simpler than other devices. This was the biggest complaint about the MyoPro. The device will be easy to take on and off, and users will not need assistance in doing so. Some devices currently on the market are too bulky and large to take off and on without help from others. The patients and users for this device can be of any age. This is the least important advantage since many patients are of the younger ages.
We looked at a series of existing patent literature as well, with the most relevant being a soft and wearable glove design, as shown, which allows for a more user-friendly and comfortable device for the user. It includes sensors on the glove that can detect the damaged area of the extremity and uses position feedback to assist as needed. The patient controls most of the movement, which is the main strength of this design. The second patented design relevant to our device was the soft polylimb system. It is wearable by the user via a backpack mount to provide enhanced object manipulation to the user. The flexibility of this design allows for the exoskeleton to be more comfortable and adjusted according to each patient's needs. The third existing design found was the exoskeleton for assisting human movement. Like the others, it is wearable and has up to 7 controlled degrees of movement per limb, ensuring user equilibrium. It can be fitted to each individual patient without requiring a functional transfer.
These questions here were a part of the survey that was created to ask customers what they thought about current available options in the exoskeleton market. Questions 6 and 7 were both open-ended questions, and the other 13 were multiple choice. The answers from question 6 as well as the 13 multiple choice were easily categorized as either positive or negative with respect to device properties such as comfort, cost, and strength. This categorization relied on the feasibility that a change to the device might be implemented. For example, question 13 asked if the exoskeleton was noisy or disruptive during use. The positive answer would have been yes, and the negative answer would have been no, while neutral counted towards neither the positive or negative count. Question 7 was omitted from categorization as it did not yield answers that fit into either the positive or negative categories. Pareto charts of both of these categorizations were created to visualize the positives and negatives from previous device properties. The areas for device improvement are seen here in the Pareto chart that was created from the negative survey results. The most pressing of the negative qualities found in current iterations include the comfort, cost, and the lag time that is experienced between user input and movement of the device. Comfort in the shoulder and elbow is especially important as it accounts for nearly 85% of comfort issues, and comfort issues clearly dominate every other issue. The positive results are seen here, and they were categorized as positive because these qualities are found to be adequate in current iterations. The least problematic of these qualities can be seen in this slide, and some of those include copay price and a lack of restriction when the device is found in use but still attached to the arm.
Like previously stated, the Pareto chart was a great tool for analyzing our survey results. We had a brainstorming session afterward to develop direction based on the Pareto chart results. This consisted of us using a whiteboard to organize our ideas and categorize what design characteristics are similar and what can be grouped together. This led to the following problem-solving tools. The interrelationship diagram allowed us to identify characteristics based on the Pareto chart and survey results and decide which were sources and which were receivers. This helped in determining which ones were more important. The flow chart was developed during our brainstorming session to outline our device's work output from start to finish. This was done to verify that we were covering all the components important to the functioning of our device. As shown, we came up with 8 customer requirements, such as level of comfort, cost, and strength of device. Narrowing down their descriptions also took a little brainstorming session between a few of the group members, and they are provided here as well. The customer requirements led to the creation of the engineering characteristics, which are similar items, but the engineering characteristics consist of more technical wording. The tables have similarities, and they are analyzed using another problem-solving tool later in this presentation, but first we will review the constraints. The possible design constraints are listed here. We've included a resource constraint, which is about the battery life and rechargeability of the battery. This constraint will be further narrowed down during device testing. The next constraint is the user-friendly constraint, which is about controlling the device by the patient or patient's caregiver. For example, putting the device on the patient and taking it off the patient. The last constraint is the electrical constraint, which is about the safety of the electrical current flowing through the device. For example, a limit needs to be set on the current to ensure components will not heat up significantly during use. This constraint will also be further defined through device testing. As of now, there are no constraints provided by the FDA. Here is the House of Quality, which is used to compare the customer requirements with the engineering characteristics and review their accuracy. As depicted, we weighted the customer requirements by the importance provided through the survey results and other problem-solving tools. We then used relationship comparisons in order to mathematically calculate the score of each engineering characteristic. These scores were used to rank the characteristics and determine the 5 key characteristics, also known as the design characteristics. The correlation between engineering characteristics is also shown at the top of the diagram and indicated as positive or negative by the plus and minus symbols. A more detailed description is provided in the report. This shows the 5 design characteristics based on the House of Quality results: adjustability, exoskeleton range of motion, lifting capacity, material cost, and minimal grading and material noise.
The functions of this device are shown in the function structure. The person reaches for the object when they want to pick it up and grab it. The person then attempts to move the object. Once the person grabs the object, the device measures muscle activity from the signals. The device then converts the electrical energy to mechanical energy, and the object moves according to the muscle signals received. The potential energy is now kinetic energy, and the person then changes direction with assistance from the device.
This brings us to the feasible concepts, the first of which is the first of the three takes adjustability into account. It does not only impact the option to customize the device to fit the individual patient dimensions, but also influences the cost of materials, the distribution of weight, the lifting capacity, and possibility of the noise of the device. The device requires an attachment point to the patient's torso to help ensure stability of each joint within the arm, and this is currently achieved through the use of a bulky vest-like attachment. This is not ideal as it is heavy, unwieldy, and difficult to put on. A backpack designed for the attachment point would allow the patient to easily slip the device over their shoulders and adjust for comfort, with multiple straps around the waist and chest. However, in exchange for a device that is easier to put on, the patient could experience a lesser range of motion above the torso due to the nature of the straps. The next concept also seeks to improve adjustability. Current designs utilize custom orthotics for the padding of the tricep and forearm areas, and although this works, it is very expensive to be fitted and cannot be reused for different patients. This concept uses air casts to press around the patient's arm, providing a tighter and more customizable fit. This allows for greater adjustability of the device as the patient can increase or decrease the air pressure using their available hand. Bladders to hold the air pressure are inexpensive and conformable with differential air pressure, meaning material cost is lessened from that of custom orthotics, and a one-size-fits-all concept can be adopted as the air pressure can be adjusted to the size of any patient. In addition, air is a compressible fluid, allowing for slight compressibility within the device and a better comfort. As with the air cast on walking boots, there is a risk of using too much air pressure and breaking the air bladders of the pump, but they are easily replaceable if this were to happen. The third concept involves reducing material noise and cost. Current exoskeleton designs use Velcro straps to secure the device to the patient, which can become problematic when you see that the strap must be replaced frequently due to the nature of how it is used in an exoskeleton. With a stainless steel mesh and magnetic attachment point, almost like that seen on an Apple Watch, initial material cost for the straps becomes greater, but the increased durability means that the straps do not have to be replaced from patient to patient. It provides greater adjustability as it can be fine-tuned to fit any size, and it also reduces noise from the device as the noisy rubbing of the Velcro material can be annoying. These stronger mesh straps will conform to all parts of the arm where they are placed and can easily be adjusted one-handed. These magnetic stainless steel mesh straps are more durable and will last longer, be easier to clean, and if aesthetic is important, provide a sleeker look to the device. Here are some screenshots of the cardboard prototype that we made, as well as the SolidWorks parts that were created and the assembly with them all together.
In order to identify the best concept design, we used an objective tree diagram and a weighted decision matrix. The Key engineering characteristics were assigned weights via the objective tree diagram, and these weights carried over to the decision matrix. Concepts were judged on a 1 to 5 scale for each characteristic, with 5 being strong and 1 being weak. We went through each concept, ranking the characteristics, and came up with the table shown at the right. Then we did calculations similar to the House of Quality to identify concept 3 as having the highest score, with concept 2 being a very close second. This design could receive further adjustability features since that is ranked as our most important characteristic.
This rehabilitative exoskeleton device would be classified as a Class 2 device. This is because it is non-invasive and there are other pre-existing exoskeleton devices out there. The powered exoskeleton device was found that is very similar to our device. It is classified as Class 2, 510K submission type, and its regulation number is 890.3480. The best pathway is the pre-market notification or 510K. Since it is labeled as Class 2, it can be marketed as a predicate device. A similar legally marketed device can be used as a predicate and document the intended uses of the products. Class 2 devices are subject to regulations by the FDA called General and Special Controls. Under the general controls, we will have to follow the quality system regulation, which is also known as the current good manufacturing practices. This is all related back to the quality assurance, making sure that the product's design, packaging, and manufacturing all meet specific standards. Some possible requirements for this device include special controls, performance standards, post-market surveillance, development and dissemination of guidelines/guidance, design controls, recommendations, tracking requirements, and other appropriate actions. Here on the slide is the regulatory pathway for device manufacturing to market display all laid out.
Our product architecture is separated into 2 different parts, the wrist and the bicep attachment. The flow of forces and energy from the arm results in the flow of signals through the sensors in the wrist attachment. The material flow in the attachment helps to better assist the user since it enables for more adjustability and movement. This adjustability is due to the sensors that can read how much support the user requires based on the flow of signals. The EMG signals are first read in the wrist attachment before going to the bicep attachment, where the EMG signals are processed for further movement assistance. The rechargeable battery that is attached to the bicep attachment allows for the device to work through its energy forces. Here we have the SolidWorks bicep and assembly drawing for our device, and the wrist attachment is built similarly to the bicep attachment. Our device has a 0.1 inch thickness with a maximum radius of 2.1 inches. The battery has a thickness of 0.7 inches with a diameter of 3 inches. The battery goes onto the bicep attachment, and there's a 2.8 inch gap between the bicep and wrist attachment to allow for space for arm movement. There are 2 small rectangular holes on the bicep and wrist attachments to allow for the strap to go through for adjustability.
The key engineering characteristics we focused on included adjustability and exoskeleton range of motion. For the prototyping processes, we plan to use ASTM and ISO standards to better develop our prototype models. Our critical design experiment and the following tests we plan to perform are listed in the table below, as well as the next one. An important component of selection testing is with computer-aided databases. More specifically, we use SolidWorks to compare different materials and run stress and FEA analysis to choose our materials.
Other considerations such as sterilization, packaging, and ethical issues must be considered to ensure that the product is developed as fully as possible. We plan to use the EO ISO 17665 sterilization method as it is compatible with most materials at a relatively low cost. The only downside is that it is a longer process than the other methods. For non-invasive devices, the sterility assurance level is FDA SAL 10 to the third. For packaging, we plan to use the ATSM D416905, which is the standard practice for shipping containers and medical device systems. As for ethical issues, our device complies with the classical regulations and standards of engineering and medical ethics. Our device will help to increase social and medical impact by aiding patients in their confidence and abilities.
The Gantt chart shown here describes the overall process for design to market regarding considerations of the FDA pathway regulations. It starts at the basic task of product specification and then progresses through all FDA regulation compliance to reach the final production phase. And here are our references. Thanks for watching.